Well, good morning. I'm very excited to be here. My name is Mike. I'm going to be talking today about AI for high productivity digital materials characterization. The material I'm showing you today won't be new to all of you, but I think I'm going to give it to you in a context that's enriching. I'm going to tell you a little bit about where we are in AI in the world today, and show you how that relates to what we're doing here at Math to Market. By way of introduction, let me tell you a little bit about myself. My name is Mike Marsh. I've been doing scientific imaging for about 25 years now. I'm very lucky to have joined Math to Market now since October, where, as it's been mentioned before, I now do work directly with the business interest in North America. Now, I've been working with and lecturing on X-ray CT, SEM, Fib, SIM, TEM for a very long time. And my expertise comes from how to maximize the extraction of quantitative information from images. So I'm happy to visit with all of you here these next 2 days about scientific imaging and image processing. My background has been in the software business, but in some applications areas where I've been doing I ran out of lines on this slide, but I go back a little bit farther than this. But I'm very excited to be here today and talk to you about this. Now, the topics I'm going to talk about today, I'm going to get to the GeoDict-AI productivity tools. But before I do, I'm going to spend about half the talk talking about the AI landscape and the modern AI boom, where we are today, and where tools like those in GeoDict fit in for context. Now, we are living in an AI boom right now, and we're hearing every day about AI. But it's constructed to use the right language. So we might sometimes say machine learning or deep learning or artificial intelligence. These terms can be easily confused, but they do have precise meaning. So I want to take a minute just to spell out those terms so that we're all on the same page. Now, what you see here is a Google image search if you just search for AI, ML, DL. But what I'll draw your attention to is if you look in the upper left corner of this slide or the upper right corner or really all over the slide, you'll see that there's widespread consensus. When we talk about this, we say artificial intelligence in the Venn diagram is a big circle that means something. And one subtopic of artificial intelligence is machine learning. And another subtopic of machine learning is deep learning. That's all widely agreed upon. And there are many, many variants of this diagram. Now, my favorite variant of this diagram actually comes from a 2016 blog post from an NVIDIA webpage. So if we all want to be on the same page, it's very clear that artificial intelligence is computer algorithms and methods that allow us to have computational systems that appear to exhibit intelligence. And this goes back on this diagram, you can see going back from the very first AI era of the 1950s. And this is a variety of tools, including some of the modern algorithms, but also any sort of algorithm that you can play a game against where it feels like you're operating against human intelligence. One subtype of artificial intelligence is machine learning, and these are all of these methods that use mathematical models that involve providing training data where the algorithm can learn from the training and then exhibit better and better performance with more training. When we talk about machine learning, we're really talking about a wide variety of mathematical models, which might be linear regression, popular tools like principal components analysis, decision tree models, artificial neuron models. And it turns out that the artificial neurons, which are the basis of neural networks, are so popular that they form their own subclass, which is deep learning. Really, deep learning is any model that has multiple layers and very importantly, hidden layers of neurons. So we have this concept of deep learning being one type of machine learning, which is one type of artificial intelligence. Now, while this diagram is quite common, this diagram I'm about to show you is all mine. So this is not a consensus. This is me telling you what matters in today's AI boom and how we got here. In this timeline, I'm going to tell you first an event from around 1990 and then what's been going on in the last 15 years. So in 1989, there were people and they were believing in neural networks when no one else did. One of those was Yann LeCun, then at that time at Bell Labs, now at NYU and at Meta and Facebook. And he and his colleagues showed the power of convolutional neural networks with a training routine called backpropagation, which enabled computers to recognize handwritten digits. This really advanced neural networks forward. If you go into a little more recent time, you'll see the work of Yoshua Bengio at University of Montreal, who incidentally was a colleague of Jan LeCun at Bell Labs back at that time. And really at that time, Yoshua showed what could be done. It's quite an esoteric mathematical concept, but this was a key advance in being able to train deeper and deeper neural networks. Then really a big watershed event was with AlexNet in 2012. Now, this work was done by Jeff Hinton at University of Toronto. And what Jeff and his co-authors showed was really the first time a neural network was so complicated that humans looking at it couldn't understand exactly what it was doing. And it showed how transformative neural networks could be in solving really important problems. Now, these three people I've just mentioned, Jan LeCun, Yoshua Bengio, Jeff Hinton, they were all actually recognized in the 2018 Turing Award. And of course, Jeff Hinton went on to be one of the winners of the 2024 Nobel Prize. Now, in the background of all of this, there were things changing. The internet was giving us larger and larger curated data sets for training. The hardware coming from NVIDIA was giving us the GPU capability of training these models. And they really created an atmosphere that took off and matured. Now, one very important event that I think goes undernoted is the development of UNet. Now, this happened just about 2 hours away from where we're sitting today, down at the University of Freiburg, through the work of Olaf Ronneberger and colleagues. They were able to demonstrate really important for scientific imaging progress in using high resolution and low resolution features from the same image to differentiate and label complicated material structures. This was relevant not just for scientific imaging, but it laid the groundwork for what we're seeing in the AI boom today. Now, maybe the most transformative event was the development of the transformer architecture. This is a really interesting paper called Attention is All You Need, written by about 6 authors at Alphabet Google. And that created the framework that tremendously kicked off the generative AI boom. Now, we're all quite focused on OpenAI when they released their first generative pre-trained transformer, what we call GPT, as an available chatbot. And then since then, there are numerous events in the generative AI boom that allow us to talk to computers using large language models, allow us to interact with large multimodal models that can process images and text. So we have the tools from Anthropic and the tools from Google Gemini and from Meta Facebook and from the new player we just learned about, DeepSeek, 2 weeks ago. But at the same time, many of you may remember when these models came out that could generate images like DALL-E and Midjourney and Stable Diffusion and Runway. Those models are also based on UNet. The reason I'm telling you all of this is UNet is the framework for scientific imaging AI that we use at GeoDict and that anyone who's trying to do modern day scientific imaging AI is using, and it's also what's driving the AI boom in these large multimodal models. Now, for context, the first time GeoDict published any use of convolutional neural networks was to solve fiber interpretation tasks. Back in 2018 was when that paper was published, and that was describing work that began even earlier. So there is this context of scientific imaging and applications that fit in the larger general AI boom that we're all going through today. Now let me spend the second half of the talk telling you about the tools and where they fit in for these AI productivity tools. So I want to talk about the AI workflow integration in materials image characterization. Now, you'll see my colleagues and I present this in our literature and in our slides quite often. When we talk about the portfolio that Math2Market offers for the GeoDict, as Andreas mentioned this morning, we have our Geo tools which generate structures. Those structure generators create the geometries from which we can make predictions on material properties. So you'll see some of these are labeled Geo for the generator, some of them are labeled Dict for the material property predictions, and there are natural insertion points for AI tools. So in the top left, when we talk about the import geo, where you bring in your scientific images, that's where you need to clean up your images to remove artifacts and where you need to do image segmentations to create those structures upon which you can do material modeling and prediction. Down at the bottom, we talk about GrainFind and FiberFind, which are necessary for labeling structures that you can then run those models on and have high fidelity definitive material characterization. So I talk about import GeoVol, the tool that allows you to use AI models for image enhancement and image segmentation. And I mentioned that image segmentation is based not only on UNet, but also some of those other non-neural network tools, some of the legacy machine learning tools, in this case, gradient boosted trees based on decision tree structures to perform that sort of image segmentation. And then we'll talk about FiberFind and GrainFind. And then you also have the GeoDict-AI framework for training custom neural networks for object identification, material enhancement, image segmentation, et cetera. So this context of GeoDict-AI productivity tools, we're going to subdivide this into these four areas: the image enhancement, the image segmentation, the GrainFind and FiberFind applications, and then we'll close out by talking about how we at Math to Market enable these tools in a differentiated, mature, and polished workflow. Now, for image enhancement, here what we're looking at is the idea of image quality enhancement, again, via deep learning. These data come from Viswasanthi Chandra down at King Abdullah University of Science and Technology. These are images of X-ray CT of carbonate plugs. The dream is to have high quality imaging and high productivity. We could always put a sample in the imaging instrument and image it for 24 hours, but that really limits our productivity. What we want is we want high quality and we want fast. If you start at the right-hand side of the slide, you can have a low quality scan with a short exposure time, and what it has going for it is that short scanning time, but the image comes out noisy and it's a low quality image. Or we could trade that off and have a long scanning time like we have in the middle, high quality scan, but which gives us the low noise and the high image quality, but now we're taking up all that time. The dream is to have all three, the short scanning time with the noise mitigated and the high image quality. This is made possible by training neural network models, which you can do with GeoDict on your own data that can take low quality, short exposure times and generate the quality of long scans. So what you see here, starting again on the left, are those low quality scans, which might be very short and very noisy. In the middle are the data they're trained against, and then on the right are the data that are derived as a result of applying the model. So you can train neural networks with these low and high quality image pairs, and then enjoy the high quality image results with the benefit of the low, fast scans. This is productive, and it's huge productivity gains across all scientific imaging. Now, the second topic I'll talk about is been very important to me for a long time. Image segmentation used to be the bottleneck in all scientific imaging workflows that I ever confronted. Now, what we're looking at right now are some FibSim images shared by Yulia Trinikima at Zeiss, where we're looking at FibSim images of a battery material, where we're looking at cathode particles and we're looking at pore space and we're looking at binder. And we want to be able to take this image, label it into its constituent parts so that we can then do material property prediction, so we can understand conductivity, we can understand diffusion, we can understand the charge-discharge cycle, and fully characterize the sample. FibSim images are notoriously difficult to process for porous materials because the nature of the imaging might mean that you see the plane you're interested in, but you might also see in the background, you can see pixels from distant slices. So we call this the pore back or the shine through. And when you look in the pores, you might see what's behind the pore, the next grain or the next binder. We only care about the plane sectioned by the ion beam, usually gallium, but maybe other materials in plasma fib. We don't care about that background material. It's also compounded by the fact, actually can be benefited by the fact that you might have two different signals, two different pieces of information, because as you're rastering the E-beam, you might get secondary electron signal, which can give you good topographical resolution, and you might get backscatter signal, in this case, the Zeiss energy selective backscatter signal, which is terrific for material contrast. So we have the SE2 images, the secondary electron image on the left, and we have the ESB image on the right, and they both have uniquely contributing information. And so we have high contrast of the structure and the foreground from the background on the SE2 image, and we have high contrast between the high atomic number materials and the low atomic materials on the right. And of course, the goal is to use a neural network model to label and reliably segment those materials between the pore space, which in this case is unlabeled, the cathode grains, which in this case is the flesh or the salmon color, and then the binder material, which is in green. And the beauty of this is that we're able to leverage the information from both of the component signals, and the user doesn't have to say, oh, in the SE image, I care about the brightness, but in the backscatter image, I care about the contrast. The model is able to learn and solve what are the coefficients needed. It learns how to differentiate and what part of the signal matters. If you look at this slide, you can see from the top panel, if we build a model based only on the SE2 image, if you look in that top red square on the right, we're missing some of the pixels because there's just not good fidelity from the SE2 image alone. But if you look in the bottom right in the same area where the red square would be, you see that we have a much more reliable image where we're leveraging the signal and the information from both channels. In the AI framework in GeoDict, you're able to use simple paintbrush tools to label material A, material B, material C. Furthermore, you're able to use tools like the GeoDict Magic Brush, which automatically partitions the image and allows you to find those contours and then rapidly paint large clusters of pixels for training. And then in this case, you can see the result of the boosted tree, the gradient boost model that completes the segmentation. Now, I want to talk about the FiberFind and the GrainFind tools. The FiberFind, again, it goes back all the way to that 2018 paper we talked about, and we've continued to refine and enhance the tool, so it's performing better than ever for randomly curved fibers with larger and varying diameters. As Martina just mentioned, you can search for a number of different cross-sectional phases of the fibers, and the model that we introduced last year, the new non-woven neural network, allows you to look at fibers irrespective of any preferred orientation, looking at multiple cross sections, and quite valuably leveraging that large diameter, in this case a 4 to 26 voxel or pixel diameter, gives a very large sweet spot for labeling those fibers. Once you've labeled the fibers, now you know the fiber diameter, you know the fiber length, you know the fiber position. You're able to characterize that fiber and then run the material predictions. This slide just talks about the validation, about how the simulated results are giving you exactly what the experiment is predicting based on the correlated experimental material for the relative probability and the volume fraction of those fibers. Now, what we hadn't shown before, and this came out in a paper that was just published last year, is we're showing the GrainFind functionality. And I'm showing images on the left of 4 different formulations of fibers that have a material phase that in this case is the binder material. The diagram on the right is just showing a proton exchange membrane fuel cell, and you may notice that going from left to right, you have multiple layers, including the gaseous diffusion layer, which is made up of material structures like you see on the left. What we need to do the material prediction, or we need to label the fibers and the interspacing material, which in this case is that binder material. So you can see what representative images look like on the left, in the gray, and then right next to it in the red and gray of what needs to be labeled for that binder phase. And that's looking at a top-down sort of an XY section. If we look over at the right, we can see the XZ sections. A1 and A2 are some example training data of what happens when I have just a foreground of fibers and binder. And then in A2, the binder actually labeled in red, that's my training data. When the model's trained on that training data, then you can see the result of the prediction in B1 and B2, where it's presented another slice of, again, just foreground, a mix of fiber and binder, and then the binder is reliably labeled in the bottom right. So GrainFind is now bringing this capability in GeoDict, again, exactly where you need it in the workflow. So this is just some of the validation that's shown in the paper. You can see on the left, you can see these solid volume fractions of fiber and binder, and you can see how they actually have some numerical correlation between those solid volume fractions. And then you can see in the panel next to that an analysis of 4 different gaseous diffusion layers, GDL1 through GDL4, where we're breaking it down into the Z abundance of binder and the Z abundance of fiber for each of those 4 materials. But importantly, at the end of the day, you have what you see on the right, which is a 3D microstructure of the foreground material that's delineated between where the fibers start and stop and where does the binder begin and end. That material characterization is exactly what you need, and that's exactly what you're getting. Now, where I want to end the discussion is in these platform differentiators. So these tools are broadly available in that there are more and more cases of, in the AI boom, of being able to talk to your chatbots and ask your image generators to do things. But what you need for these scientific imaging workflows are not those generalized tools. You need the specialized AI tools for scientific imaging that are polished, mature, and fit natively in your workflow. The ease of use is key, and the fact that GeoDict makes that workflow integration friendly and appear in the right spots is where you're going to derive great value from adopting that part of the GeoDict portfolio. Now, the next point is a bit esoteric, but it's a huge benefit. The fact that our team has migrated from one solution technology, the Alphabet Google TensorFlow stack, to the Meta Facebook PyTorch stack. What this means for end users is you're able to leverage multiple GPUs, you're able to leverage the latest GPU hardware, and not have the software out of date or being unable to support the latest hardware. Another major benefit is that GeoDict actually allows you to leverage multi-GPU support for both phases of the deep learning lifecycle, both the training and the inference. And so because we've built the infrastructure, used the right tools, and made it friendly, you're able to leverage all those benefits without any expertise. Finally, I just want to mention this creates key value in scientific imaging experiments where you want to leverage multiple channels or signals of information, which in SEM and in FibSim might include backscatter and secondary electron, or might even include concentric ring detectors where you're looking at different quadrants. In the case of X-ray CT, such as dual energy CT, where you have high KV scans and low KV scans, or even images like bright field micrographs where you have red, green, and blue, and you want to leverage all of those signals. And again, the key thing is the user doesn't have to know, is the value in the green, is the value in the red, what are the different contributions? The neural network models learn all of that and figure it out for you. So I'm going to stop there. I look forward to talking with all of you these next 2 days. If you want to talk at all about AI, you can tell it's something I'm very interested in, whether it's machine learning or deep learning, but I'd love to talk to you more about all of these topics. So with that, I'll step back and take any questions you have on this or anything else.